Imagine spending $1.8 billion to build the most advanced supersonic bomber in aviation history, only to watch it fall out of the sky because of a piece of steel the size of a water bottle. In the spring of 1968, the United States Air Force deployed the General Dynamics F-111 Aardvark to Vietnam under the Combat Lancer program. Within 6 months, 5 of these technological marvels smashed into the jungle floor. Not a single one was brought down by enemy anti-aircraft fire or surface-to-air missiles. Instead, they were annihilated by a catastrophic mechanical failure hidden deep within their own architecture. Let us execute a complete 3D digital teardown of this $1.8 billion machine to expose the exact mechanical nightmare that doomed the F-111 on its first day of combat. Initiating wireframe transition on the outer fuselage, we will strip away the radar-absorbent paint, the honeycomb aluminum paneling, and the titanium shielding. Deleting the twin Pratt and Whitney TF-30 afterburning turbofan engines, which combined generate 37,000 pounds of thrust. Bypassing the revolutionary terrain-following radar system located in the nose cone. Let us isolate the primary structural anomaly located dead center in the airframe, zooming in on the variable sweep wing mechanism. This hydraulic beast allows the wings to sweep from a fully extended 16 degrees for maximum lift during takeoff, all the way back to a lethal 72.5 degrees for supersonic low-altitude penetration. However, the entire aerodynamic load of a 47-ton bomber flying at Mach 1.2 is channeled directly into a single highly localized focal point. Make the surrounding aluminum alloy transparent and highlight the wing pivot pin. You are looking at an 8.5-inch long drop-forge steel rod. This single unassumingly small mechanical joint carries the life or death of the crew. Let us analyze the extreme aerodynamic stress inflicted upon this precise location. Put the aircraft into a simulated attack vector flying 50 feet above the ground at 900 miles per hour. The aerodynamic lift generated by the massive swept wings creates an upward bending moment of immense magnitude. Simultaneously, the sheer weight of the fuselage pulls downward. This opposing physical action generates an extreme shear force directly across the transverse axis of the pivot pin. To put this into perspective, imagine hanging 3 fully loaded semi-trucks from a single steel bolt while simultaneously vibrating it at high frequencies. That is the exact mathematical baseline of the pressure exerted on the F-111 wing pivot pin during a standard evasive maneuver. Now let us perform an X-ray microstructure scan directly into the atomic lattice of this component. The pin is manufactured from D6AC steel, an ultra-high-strength, low-alloy steel originally developed for missile motor cases. It boasts an incredible tensile strength exceeding 220,000 pounds per square inch. On paper, it is indestructible. But let us execute a cross-section cut on the molecular level. During the intense drop forging manufacturing process in the factory, microscopic irregularities occurred. The rapid heating and cooling cycles trapped minuscule non-metallic inclusions within the steel matrix. These are tiny microscopic air pockets and slag impurities hidden deep beneath the polished metallic surface. In mechanical engineering, we call these stress concentration points. They are essentially microscopic ticking time bombs waiting for the right amount of physical leverage to detonate. Let us rewind the simulation and examine the exact metallurgical failure in the D6AC steel forging process. D6AC requires a highly complex multi-stage heat treatment to achieve its legendary toughness. the raw alloy is heated to 1,650 degrees Fahrenheit, held until the carbon fully dissolves into the iron matrix, and then rapidly quenched in salt baths at 400 degrees. However, if the cooling rate fluctuates by even a fraction of a percent, the resulting martensitic structure becomes dangerously brittle. We can observe the grain boundaries within the steel using our digital electron microscope. Notice the dark jagged lines intersecting the smooth crystalline planes. These are manganese sulfide inclusions. When the immense aerodynamic shear force of a Mach 1.2 dive hits the pin, these inclusions act as wedges. They amplify the ambient stress by a factor of 3. The internal pressure around these microscopic flaws spikes to over 300,000 pounds per square inch, easily surpassing the ultimate tensile strength of the surrounding metal. Under static load in a laboratory, these microscopic flaws remain dormant. But the reality of combat over the Vietnamese jungle is a brutal, relentless onslaught of dynamic physics. Every time the pilot commands the wings to sweep forward or backward, massive hydraulic actuators slam thousands of pounds of pressure against the joint. Every time the aircraft hits a pocket of turbulence or executes a high G pullout to avoid a mountain peak, the wings flex. This relentless mechanical oscillation creates cyclical stress. Let us isolate a single microscopic inclusion measuring less than 1/10 of a millimeter. Watch closely as the metal fatigues over time. With every high G turn, the atomic bonds at the edge of this microscopic void are stretched beyond their elastic limit. The bonds sever. A microscopic fracture is born. We call this fatigue crack propagation. This crack does not happen overnight. It is a slow, insidious mechanical disease. It spreads outward through the D6AC steel, cutting through the crystalline structure of the metal like a microscopic blade. Because the crack grows internally, routine maintenance inspections completely fail to detect it. The mechanics on the ground see a perfectly intact, polished steel pin. But inside the cross-sectional area capable of bearing the load is shrinking by the minute. The structural integrity of the $1.8 billion machine is deteriorating silently with every single flight hour logged. The stage is perfectly set for an inevitable physical collapse. The engineers designed a wing sweep mechanism that relied heavily on theoretical perfection, completely underestimating the brutal reality of mass manufacturing tolerances. The sheer arrogance of relying on a single point of failure without a redundant backup system highlights a fatal flaw in aerospace engineering. They consolidated the extreme forces of supersonic flight into a single 8.5-inch bottleneck. Let us fast forward the simulation to the dense, humid skies over Southeast Asia in the spring of 1968. The F-111 is conducting a low-level terrain-following bombing run under the cover of absolute darkness. The aircraft is hugging the jagged mountainous topography at an altitude of just 200 feet, utilizing its revolutionary TFR radar to automatically adjust altitude. The pilot spots a sudden sheer cliff face ahead and pulls back hard on the control stick. The twin Pratt and Whitney T F-30 turbofan engines roar at maximum afterburner thrust. The aircraft violently pitches upward into a high-G evasive climb. At this exact microsecond, the mechanical load concentrated on the variable sweep wing pivot pin reaches its absolute mathematical zenith. Let us zoom back into the atomic lattice of the D6AC steel pin. The cyclical loading from months of rigorous flight testing and the brutal extreme G combat maneuvers over the jungle have pushed that microscopic fatigue crack to its critical threshold. The structural integrity is compromised. The remaining healthy crystalline steel can no longer distribute the immense localized aerodynamic shear force. Suddenly, a violent acoustic snap echoes through the heavy mechanical linkage. It is the terrifying sound of ultra-high-strength forged steel completely surrendering to the laws of physical leverage. The 8.5-inch pivot pin completely shears in half along the transverse plane. In an instant, the vital physical connection between the massive 47-ton fuselage and the right wing is permanently severed. The explosive decompression of the internal hydraulic actuators sends a massive shockwave rippling through the aluminum honeycomb airframe. Deprived of its primary structural anchor, the massive swept wing violently rips away from the fuselage, trailing a chaotic plume of vaporized hydraulic fluid and highly flammable aviation fuel. Immediately, the F-111 experiences a catastrophic and fatal loss of asymmetrical lift. The intact left wing is still generating tens of thousands of pounds of upward aerodynamic force, slicing through the dense, humid air. Conversely, the right side of the aircraft is now generating absolutely zero lift. This extreme physical imbalance instantly throws the supersonic bomber into an uncontrollable violent barrel roll. In aviation mechanics, we call this an unrecoverable death spin. The aerodynamic drag coefficient skyrockets exponentially as the asymmetrical mutilated airframe tumbles through the atmosphere at Mach 1.2. The immense centrifugal force generated by this violent high-speed rotation subjects the entire airframe to over 12 Gs of lateral acceleration. To understand this level of physical violence, imagine being strapped to the outer edge of a massive industrial centrifuge, spinning at maximum velocity while simultaneously crashing through a solid concrete wall. The G-force is so severe that it begins tearing secondary access panels and radar equipment directly off the nose of the aircraft. At this critical juncture, standard military fighter jets would rely on individual 0-0 ejection seats to save the crew. But the F-111 was engineered differently. It was designed to be a pressurized high-altitude supersonic bomber. Instead of traditional ejection seats, it utilizes a highly complex integrated escape capsule. The entire cockpit section, containing both the pilot and the weapons systems officer, is designed to physically sever from the main fuselage and launch into the air propelled by a massive 40,000-pound thrust, solid-fuel rocket motor. Let us execute a 3D cross-section cut of the cockpit module to observe this intricate mechanical ejection sequence. The pilot desperately pulls the yellow ejection handle located between his legs. An electrical signal instantly travels through the wiring harness to a series of explosive bolts designed to cleanly detach the capsule from the airframe. However, the aerospace engineers completely failed to account for the extreme physics of a supersonic asymmetrical death spin. The massive centrifugal force generated by the tumbling aircraft physically warps the primary titanium airframe. The explosive bolts successfully detonate, but the mechanical steel guide rails of the escape capsule are severely twisted and jammed by the immense lateral pressure. Furthermore, the crew is currently experiencing sustained negative G-forces, pinning them brutally against the plexiglass canopy and completely restricting oxygenated blood flow to their brains. The 40,000-pound thrust rocket motor successfully ignites burning at over 3,000 degrees Fahrenheit. But it simply cannot overcome the mechanical lock created by the warped fuselage. The escape capsule remains inextricably trapped inside the disintegrating bomber. The highly advanced multi-million-dollar safety system has been completely neutralized by raw kinetic energy, effectively transforming the reinforced cockpit into a titanium coffin, plummeting toward the jungle floor. The devastating loss of 5 highly advanced aircraft in merely 6 months forced the United States Air Force to immediately halt combat operations and ground the entire F-111 fleet worldwide. The subsequent metallurgical teardown and investigation revealed a horrifying truth. The most technologically advanced and expensive bomber in human history was being systematically destroyed by microscopic impurities measuring less than a fraction of a millimeter. Because standard ultrasonic and X-ray maintenance inspections could not reliably detect these minuscule subsurface flaws deep within the forged steel, the military had to invent an entirely new, radical method of stress testing. They developed a procedure known as the cold proof test. Let us transition the 3D environment from the jungle to a specialized, heavily insulated, climate-controlled hangar. Every single F-111 in the inventory was rolled into this freezing testing chamber. The ambient temperature was artificially plummeted to a bone-chilling -40 degrees Celsius. At this extreme sub-zero temperature, the D6AC steel loses its natural elasticity and becomes highly brittle, magnifying any internal structural flaws. Massive industrial hydraulic jacks were then securely attached to the variable sweep wings. The engineers systematically applied upward and downward mechanical forces that far exceeded the standard aerodynamic combat loads. The engineering logic was brutally simple and unforgiving. If a steel pivot pin possessed a microscopic manufacturing defect, the extreme cold combined with the massive hydraulic pressure would force the crack to propagate instantly, causing the pin to shatter right there inside the safety of the hangar. The military literally had to intentionally break their own multi-million-dollar aircraft on the ground to prevent them from snapping in the air. The General Dynamics F-111 Aardvark eventually evolved into a highly effective long-range strike aircraft serving for decades. But its disastrous combat debut in 1968 remains one of the most vital and sobering case studies in aerospace engineering history. It stands as a terrifying physical reminder that in the unforgiving realm of supersonic physics, there is absolutely no such thing as a minor manufacturing defect. You can design an aerodynamic masterpiece utilizing the most sophisticated terrain-following radar systems on Earth. You can spend $1.8 billion pushing the absolute boundaries of military aviation technology. But the exact moment you decide to consolidate all of that immense aerodynamic pressure into a single localized mechanical bottleneck, you are placing your entire mission at the mercy of mass manufacturing tolerances. A microscopic pocket of air trapped inside a cheap piece of steel during a factory forging process was all it took to overpower and ground the entire engineering might of the United States military. If you want to continue exploring the fascinating and often catastrophic mechanical failures that shaped the history of military aviation, do not forget to subscribe to DEFUNCT and leave a comment below on which legendary war machine we should tear apart next.